This one. There we go. Hello, everybody. Thank you so much for coming to the first lecture of the Fall 2024 Astronomy Lecture Series. As you may know, I'm Jillian Epstein, the Outreach Coordinator this year, and I'm so excited to introduce our first speaker of the semester, Francisco Blanco. Francisco Blanco is a last-year PhD student in physics working under Professor Flanagan, and most of his work centers around gravitational waves and how we detect them. I shall hand it over to you.
Hello, everyone. I'm Francisco, PhD student, and I'm going to talk a bit about black hole collisions and the gravitational waves they emit. Before I start with that, maybe some comments about the big picture. The universe is a wild place with things such as big balls of fire that are fusion reactors that give us energy that explode into supernovas that can be billion of times brighter than stars. When stars leave their cycle, they can also transform into a black hole, which can suck the surrounding gas with so much strength that they shine brighter than 10,000 galaxies. On top of this, the universe started with a Big Bang, which is the most extreme event in the universe, and it shines up to this day. And on top of this, when you have two black holes, they can collide. And all these things have in common that they are the most extreme events in the universe, and they emit stuff. That's the main takeaway. So let's go over the pictures again, because they're so pretty. The sun emits light in the visible range, UV, infrared, we know all that. It also emits neutrinos. There's 100 trillion neutrinos going through your bodies every second. You just don't know because they don't interact with anything. Supernovas emit high energy particles, protons, electrons, gamma rays. We would be fried if one happens close by. Quasars, which is a black hole that is sucking all the gas around it, are like supernovas turned to 11. And then the Big Bang emitted a bunch of stuff that we can still detect up to this day in the form of the microwave background, which is so stretched by the expansion of the universe that it's just microwaves, but we can still detect it. And all this reminds me of a comic by, what's his name? XKCD. Do you know it? Yes, of course you do. So in the y-axis is the electromagnetic spectrum, in the x-axis, the sound, the frequencies of sound, and the tiny, tiny square is what we can see and hear. So we are mostly blind and deaf, and that should have many, many more axes, because we can't see neutrinos, we can't see high energy beams of particles, we can't see dark matter, we can't see things that we don't know we can't see, that we don't even know what they are, and we can't see gravitational waves. Which brings me back to the last picture. These are a bit less shiny, maybe, because they don't emit light, it's two black holes, but they emit a bunch of gravitational waves. And until 2015, the first detection of gravitational waves, we didn't even know they existed for sure. And now we do. So the moral of the story is that we need to build detectors to have information about these extreme events. Like the answer to quantum gravity could be like going through this room right now, and we don't know because we don't have the detector to measure that. So with this introduction, let me give you a quick summary of the talk. First, I'm going to talk about two-body problem in the Newtonian context, Kepler, Newton, and then the two-body problem in Einstein theory of general relativity, how that implies the existence of gravitational waves, which sources are the most important and the most relevant for us to find gravitational waves, and how do these waves look, how do we detect them, and why they're interesting. So a bunch of things. And if anyone has any questions, you can stop me halfway through. I don't mind. I think we have time. Good? Amazing. So the two-body problem started, well, I picked kind of a random date because it started with Galileo and there's many other observations before, but Kepler is the first one who gave rules for how two-body systems move. A two-body system is the moon and the earth, or the earth and the sun, or Jupiter and the sun, or any two objects that interact gravitationally. And he gave what we call phenomenological rules, which is we don't know why, but these are the rules. It's like, as if you go out, you see an apple fall, and say, okay, apples fall. And then you go and see an orange falling, and say, okay, oranges fall too. But you don't know why that's happening. You just have a series of observations, which were orbits are ellipses, the periods and the radii of the orbits satisfy certain rules. And it wasn't until Newton, when he gave the universal law of gravity, that all those observations were unified with the motion of objects on Earth. And we found an explanation for why these things were happening. However, this is the force, by the way. So the force between two objects is the product of the masses over the distance between them. And there's a Newton constant over there. There's a square missing there, I think. That's the potential. The force is a square. There's problems with this force right away. First problem is that it knows instantaneously where each object is. So if that force were to describe the force between the sun and the earth, and someone pushed the sun a tiny bit to the left, we would feel it immediately. And even before general relativity, Einstein taught us that that's wrong. There should be a delay because there's a speed limit in the universe, and information also must obey that speed limit. But there's another problem, which is that this disagrees with some observations. For example, the precession of Mercury, which hopefully I'm going to show you right now. There you go. So Newtonian physics predicts an elliptical orbit, but if you watch Mercury for like 100 years, it kind of shifts a bit. And this is my favorite part about the story, because the orbit shifts by 5,000-ish arc seconds every century. And people thought, okay, it's probably just Jupiter is pulling too much. It's messing up our two-body system into a three-body system. And that is almost right. The pull of Jupiter explains 5,558 arc seconds, and there's 42 missing, which in every other discipline, that's success. That's a win. Just take the win and move on. Like, that's it. But here, people were, okay, there's 42 arc seconds missing. How do we explain them? And at first, they thought, okay, there has to be another planet, which was called Vulcan, and they thought it was closer to the sun than Mercury. And before you say, oh, these dumb astronomers, they didn't know anything, a few years before, they saw that Uranus was doing a weird thing, and they predicted for sure there's another planet, and they found Neptune. So, yes. An arc second is how much a star moves in a second in the sky, that angle. I have no idea how to convert it to other units, but astronomically, it's the tiny angle there. So, thank you for the question. What was I saying? Yeah, they found Neptune with that argument. So it was not that wrong. But in the end, Vulcan was not there, and Einstein included the tiny, tiny corrections of general relativity and found exactly 42 arc seconds in 1915. And that was the first win for general relativity. Any other questions about Mercury? No? Good? Amazing. So Einstein's theory of gravity is the curvature of space-time. I won't go into more details than this beautiful animation. You have a big object, it bends space-time. The secondary object is not feeling any force. There's no force of gravity, no forces, doesn't exist anymore. The secondary object is just trying to follow a straight line, but space-time is curved. So the straight line looks weird to us, and that's why it's going in circles. And that explains all the predictions of Newtonian gravity and the corrections. But I'm talking about Newtonian gravity and Einstein gravity, and I'm saying, okay, Newton was wrong, Einstein was right. So what is the difference between these two types of orbits? Newtonian orbits are closed, meaning that they loop back to where they started. They stay on a plane. If you started on a plane, stays there, and they are elliptical. Einstein orbits are a mess. Let's see if I can do this animation as well. There you go. That's a generic orbit around a black hole. So it's open, it doesn't loop back to where it started. It has polar motion, meaning that the orbit wobbles in the polar direction. It has periastron advance, which is a fancy name for the thing that was happening to Mercury. And maybe it's chaotic, we don't know for sure. Chaotic meaning that if you change the initial conditions a tiny bit, you get something completely different. So the question that you might have is, if Einstein was right and Newton was wrong, and if these are the orbits that Einstein predicts, why is the solar system so nice? Like, why is it ellipses and not this horrible mess that keeps going forever? This is not looping, this is just a long animation. Beautiful. So the key idea is that physics is all about knowing what effects to neglect. Okay, so what can you forget about? How to simplify the problem without losing accuracy. For example, if you're moving much slower than the speed of light, you don't need relativity. You're good to go with Newtonian physics. Doesn't mean that Einstein was wrong. It's just that the corrections are too small. If your inertia is much, much bigger than the viscosity of the air, you can forget about air drag. If you throw a bowling ball through the air, you don't need air drag in your equations. If you throw a feather, you do need air drag in your equations. Similarly, if the length scale of your object is much, much bigger than the size of an atom, quantum mechanics, not important. And the last one, which is the one that concerns us, is that this one is a bit abstract, but if the distance between the two objects is bigger than the size a black hole would have if you mashed those two objects into a black hole, then you can forget about general relativity. And that is why Mercury is the only one that had a weird correction, because it's the closest one to the sun. All the other ones are far enough that general relativity doesn't matter at all. And Mercury is the first one that is close enough that this number is bigger than 1, but not that much bigger. So you get a correction of 42 arc seconds. So I want to give some details about more the mathematics of how we model two-body systems and a tiny kind of glimpse into research, and without saying too much more than that. We study the two-body problem in regimes that simplify the math, because the two-body problem is not solvable in GR. You cannot just solve Einstein's equations. There's a joke that a professor told me once, that is, Newtonian physics can solve the two-body problem, but the three-body problem can't solve. Einstein can solve the one-body problem, but the two-body problem can't. And string theory can't solve even the one-body problem. So what we do here is to simplify it in some regime where we can solve it. So for example, if the two objects are really far away, it's almost Newtonian physics. And then you use post-Newtonian theory, which is what Einstein used for Mercury. It's just Newtonian plus a tiny relativistic correction. On the other axis, we can assume that the secondary object is much, much smaller than the first one. For example, if you have a neutron star orbiting a supermassive black hole. And then the secondary is not really relevant. It's almost just like a one-body system with a tiny correction from the secondary. And that's the area where I work in, by the way, if anyone has any questions about that. And then lastly, if all the things in the system are the same order of magnitude, you can use numerical relativity, which is just putting it into a computer. If there's too many different scales in the problem, computers don't work because they need to resolve many different scales and the errors just accumulate too much. So computers are best when the distance is not too big, not too small, the masses are not too big, not too small, and everything is order 1 in some units. Okay, but this is all very nice. How do we check these models? We have these approximations. How do we observe these systems and we check? Well, gravitational waves are the perturbations on space-time sourced by these accelerating masses, by two-body systems. Here's another cute animation that is not very realistic. I don't think this is how it should look, but it looks cool. So here it is. So this is what it is. When you have two objects orbiting one another, they ripple through space-time. Those ripples propagate at the speed of light, and we can hopefully detect them here. So what are the main sources or the strongest sources of gravitational waves? So let's play a game. So which one is number 1, you think? The biggest, strongest? Yes. That is a really good guess, but it's too far away. I don't think we can detect that. That would be, you should write a grant and propose to measure the gravitational waves of the Big Bang. Yes, I think it's too far away. But yeah, that is the biggest source of gravitational waves. After that, yes, black holes. And this cute drawing, I'm sure you saw it in the past or in Interstellar. I really like it. The accretion disk of a black hole is actually a disk. So the orange thing on top and on the bottom shouldn't be there. It's just going to be a black hole now. It has something orbiting around. Because it's so heavy, the light of the part of the disk in the back is shooting in this direction, and the black hole is bending it like this. So you're seeing the back of the black hole, and that's why it has orange on top on the bottom, but it's just a disk. Very good. What is the number 2 object? Yes. Neutron star? Yes. Very cute. Neutron stars are the second most compact object. And what is the third place? Yes, white dwarfs. Perfect. Very good. So let me give you a bit more information about these objects. So here's just some information that I think is cool. On the first column, I have the mass in units of the sun. So 1 is weighs as much as the sun. Second column is typical size, just on average how these things, how big they are. And the third column is my favorite, is how much does a spoonful of this thing weight. So white dwarfs, kind of impressive. They are the size of the Earth, but a spoonful weighs as much as an elephant. That's cool. Neutron stars are as big as a city, I guess, 10 kilometers. Is that Ithaca? Probably. And a spoonful of neutron star weighs as much as Mount Everest. So that's crazy. And the reason for that is very cool, because most matter is empty space, because atoms have the nucleus, a bunch of empty space, and then electrons. Neutron stars are what happens when all the electrons and all the protons are gone, and it's just neutrons packed throughout. It's just a soup of neutrons without any space in between. And that's why they're so dense. And then we have stellar black holes, which have masses from 3 to 50 masses of the sun, which form from a star. And they're empty space. So a spoonful is meaningless. If you try to get a spoonful, you lose a spoon. So it doesn't make too much sense to talk about a spoonful. And then we have supermassive black holes, which are 50,000 to billions of masses, the solar sun, the mass of the sun. And we have a gap in between that I'm sure people here know more than I do, because I don't work on astrophysics, but it's a bit of a mystery why we don't see black holes in between. We have the ones that clearly come from a star, and the ones that clearly have been around for a long, long time, and nothing in between. So that's weird. And that's all I'm going to say about that, because I don't have the answer. Okay, so how do we detect gravitational waves? Yes. Yes, good. Thank you. Exactly, with an interferometer. So I'm going to explain quickly how this works. You throw a laser into a beam splitter. The beam splitter splits the beam, over and on, into two mirrors, bounces back, and then hits the screen. If one of the arms is longer than the other one, the beams are going to get out of phase. And then instead of seeing a white dot on the screen, we're going to see a black dot on the screen. Yes. Yes. Well, yeah, they were trying to prove that ether existed, which they were so wrong. But the experiment is amazing, so good for them, you know. So originally the experiment, if you do it in a lab or if you're trying to do optics, you tweak the length of the arms yourself. Instead, here, we let the length of the arms to be the same, and we wait for a gravitational wave to go by. And because gravitational waves are ripples on space-time, if a gravitational wave goes through, it's going to stretch and contract the arms, and you're going to end up seeing an interference pattern, even if you set up the arms to be the same length originally. This has been done in the LIGO collaboration, which is exactly that, which I find amazing, that this experiment who costed, I don't want to know how many millions of dollars, it's just a big version of the thing you do in the first year of undergrad physics. I think it's amazing. But the arms are 4 kilometers long, but it's still basically that. I don't want to get too technical, but there is an important part of gravitational wave detections, that is the frequency sensitivity of the experiment. Because LIGO is underground, any seismic motion of the Earth, any car going through, the waves hitting the shore 1,000 kilometers, that's all low frequency noise. So the frequency sensitivity of LIGO is between 10 and 10 to the 4 hertz. Because of that, and because the frequency of the waves is inversely proportional to how heavy the system that is emitting them is, LIGO detects stellar mass stuff. So 2 stellar mass black holes, or 2 neutron stars, or 1 neutron star and 1 stellar mass black hole, but it's all the same mass. It's some 3, 5, 10 solar masses. The next generation of gravitational wave detections is LISA. Hello. And my favorite letter in LISA is S, because this is in space. This is kind of like an interferometer with 3 arms instead of 2. Don't ask me why 3 is better than 2. That's for the experimentalists. But this thing is going to be floating in space, in a Lagrange point behind the Earth, just going around, following the Earth. And because of that, it has no earthly noise. There is no earthquake, no like car going by. So the frequency sensitivity is much lower. So it can detect much heavier things. So it can detect collisions from supermassive black holes, which are millions of times the mass of the sun. But because of that, the signals are months long as opposed to seconds long, like in LIGO. So a problem that probably some of you will have to figure out is how to tell the signals apart, because we're going to receive a bunch of gravitational waves all together, all mushed up, and someone will have to do the data analysis to recognize, okay, this one came from here, this one came from here, because they're all going to overlap. So how do these waves look? This is kind of an accurate thing that came from a paper. Initially, you have the 2 objects in spiraling, and as they in spiral, they emit gravitational waves, so they lose energy, so the orbit shrinks. Because the orbit shrinks, the frequency gets higher and higher until they merge, which is the peak here in the end. And then you have the ring down, which is my favorite part, because it's like hitting a bell and hearing the overtones of the bell. Once the 2 black holes collide, you get a ringing black hole that emits waves until it settles to its new equilibrium position. So people refer to doing spectroscopy of black holes as equivalent to when we were doing spectroscopy of the hydrogen atom and figuring out quantum mechanics for the first time. Now we are figuring out gravity for the first time with these types of experiments. But this is actually not at all how it looks. This is much prettier. Yes. Yes. So let me explain every part of this plot. X-axis, time. We are good with that. Y-axis is strain, which is literally how stretched the arms are. It's the strain that the arm is suffering. Strain is a word that comes from like material science and like the stretching and deformation of things. So it's that. And then this tiny box just shows you the separation of the black holes and the relative velocity. So you see that they get really close and they speed up really fast. So good, thank you. Any other questions about this plot that is kind of accurate, but not really? Okay, so the more accurate version of the plot is actually like this. So there's a lot going on. The black thing is actually the strain that we measure, which is really ugly and covered in noise. The purple, I guess it's purple, pink thing is the template. So it's our guess. We do the theory and we predict that it's going to look kind of like that. And then this blue thing is kind of like the product between the two. It's filtering the noise with our guess. So the idea is that you put your guess through the noise, and if hidden in the noise, there's something that looks like your guess, the blue one should go up at some point. There you go. That's a detection. That's what they saw when they found the first gravitational wave. So because of this, it's really important to have good theoretical models. It's a bit of a weird take on the scientific method because you need to know the answer before you get it, which is not really how science works, but it's the best we can do. And the reason why this actual strain is just a bunch of noise is because of our experimental noise, because of the cars driving by LIGO, but also because there's many events that emit gravitational waves. And we are just trying to measure the specific wave coming from one binary system. But there's a background gravitational wave. There's many two systems. Everything emits gravitational waves. So that's why we have a mess over there. And this is why there's many different communities in the gravitational wave detection endeavor. There's experimentalists who build LIGO, but also LISA in the future. LISA launching in 10 years and has been approved for funding. And I think they sent their Pathfinder mission. So they sent a tiny probe to check that the place where they're going to put the detector is fine and everything went well. So yeah, those are the experimental groups. They also collect the data, analyze the data. Probably data analysts would kill me because I put them in the same category as experimentals, but I'm a theorist, so I don't care. Then there's numerical groups that really focus on the simulations, and they take some information from theoretical groups, data from experimentalists, and they gonna mix it up when theory alone can't really do anything. And then there's theory groups that study more the foundations of the two-body problem, and we use different approximation schemes for different regimes, like what I said in the beginning. If the objects are too far away, you can use post-Newtonian theory. If one object is much heavier than the other one, you can use the self-force formalism, and so on. And the theoretical groups provide the templates that the experimentalists need to use to filter through the noise. So it's a big collaboration. So I'm getting into final section of the talk. I want to explain a bit why this is cool. I mean, I think it's cool on its own, but it also has implications that make it cooler. So we can get information about general relativity, about whether our best theory of gravity is correct or we need to modify it somehow. We can get information about black hole horizons and what's up with them. We can get information about exotic matter, which is the physics inside neutron stars. And we can get information about the shape of the universe. So how quickly it's expanding and all that. So let me get a tiny bit more into detail in each one. So the way you check a theory is by pushing it to the limit of the theory. That's what happened with Mercury and Newtonian physics. And black hole collisions are the most extreme event we can observe in the universe. So hopefully, when we get gravitational waves coming from black hole collisions, we can find deviations from general relativity. And there's a big industry of people just dreaming crazy theories that are general relativity in extra dimensions, or general relativity with extra interactions, or general relativity with a Newton's constant that changes in time or that changes in space, or gravity that is actually holographic and actually we live in one less dimension than this, and string theory, quantum, like loop quantum gravity. There's many modifications to gravity, and hopefully if we can find deviations from Einstein's theory of gravity in these detections, we can know which path seems the best, I guess. Another thing we can explore is exotic states of matter. I talked a tiny bit about this, but let me say a few more things. In the life of a star, there's always a competition between gravity pushing everything in and different forces that resist that. When the star is still on fire, it's just the pressure of radiation, but once the fuel is used, you have different forces. And in the end, the last force is just this quantum force that prevents identical particles from occupying the same space. It's just like an identity crisis of the particles. So they cannot be at the same spot because then they would be the same particle. And that quantum mechanics doesn't like that. It's called Fermi pressure. And that's the, yes, that's it. And that's the only thing preventing neutron stars from collapsing. And because of that, they have the biggest pressures in the universe. And their insides are this super packed lattice of neutrons, and sometimes this soup of gluons and quarks, which are the things inside neutrons. And we have never seen matter in these states. Like we know Bose-Einstein, condensate, plasma, all the fancy things, but this one is new and weird, and we don't know how it works at all. Like a soup of gluons and quarks, that's new. So because neutron stars are made of this weird soup and they interact with the other partner in the binary system, their equation of state gets encoded in the gravitational waves. And when we measure the gravitational wave, we get information about what's going on with this soup, which is not just cool for astrophysicists, but it's cool for particle physics, for just fundamental physics in general, because we don't fully understand quarks. So this is a cool application that mixes gravity with other things. Then there's black hole horizons, which would be a whole separate talk. I'm just going to say a few things. There's the no-hair theorem that tells us that black holes are described by their mass and spin and nothing else. So all black holes are identical, and they look kind of like fundamental particles in the sense that the differences between particles are just how heavy they are, how fast they're spinning, if they have electric charge, and that's it. But this no-hair theorem sometimes gets a bit modified in modified theories of gravity. And also it might be a solution to the black hole information paradox, which is something else completely. If the black holes have hair, maybe that's a solution. So gravitational wave detections are a way to test this in the following way. Once the two black holes collide, the gravitational wave tells you the information about the initial mass and spin of both black holes. But then the ring down, these like overtones of the remaining black hole, should depend only on the mass and spin of the black holes that formed this remaining black hole. If that's so, then no-hair theorem works, and the last state is only a function of mass and spin. But it could be that there's more information encoded in the black hole horizon that we don't really understand. And this has to do with holography, with quantum mechanics, with Hawking radiation, and many other cool things that you can ask me about if you want, but that's all I'm going to say. And the last one is the shape of the universe. So our current understanding is that dark energy has a constant density, which is a bit ambiguous because it per meter cubed, it's always the same, but the universe is expanding, so there's always more cube meters. So constant density, but it's bigger and bigger with time as a whole. And it's what pushes the expansion of the universe. But there's different alternatives where dark energy is not constant, it changes in time, it changes in space, and it's made of actually some field with some degrees of freedom or something else. And gravitational wave detections give us information about this. We can test our theories about dark energy with gravitational wave detections. And I think that's all I wanted to say. So I'm going to leave you with questions and the simulation of two black holes colliding. Thank you very much.
Second round of questions, I'm actually bring a microphone around just so people know it's working.
You need to, I think, press the for a long time.
Working now. There we go. Okay, I'm gonna bring the microphone around so people on Zoom can hear the questions being asked. Also, if people on Zoom want to ask questions, they can just type them in the chat. I don't think they can see me, but that's okay. So I'll go over there for our first question.
Testing. Okay. This is more like two questions. The first one being like, what was your reaction to the June 2023 detection of gravitational waves via the neutron star array?
Was my reaction?
Like, were you excited about it?
I'm always excited about gravitational waves. Yes. I work really on the theoretical side of things. So I see gravitational waves in the newspaper like any other person. I'm not like in the side of experiments. So I don't get the tip before it's going to happen or anything. But I think it's really cool. I'm mostly interested in LISA more than LIGO, just because LISA is going to detect supermassive black holes, which I find cooler. But yes.
And then my second question, which is more related to that. So there's been a lot of speculation on what potential might arise from better detections of low frequency gravitational waves, which are like harder to detect sort of. One question that was like raised back like last year when it happened was regarding the formation of the universe in the initial 300,000 years where the universe was sort of opaque because of how dense it was. Do you believe or perhaps entertain the chance that gravitational wave interferometry could reveal information that was hidden to us before the CMB started releasing?
I think it's really optimistic.
It's optimistic.
I mean, I would love to be surprised. That sounds cool, but I think it's too optimistic. The things that we're going to detect with LISA, which is low frequency gravitational wave astronomy, is supermassive black holes and low frequency phenomena in gravity. For example, memory effects, which are something really cool that I can talk about. But I think that if you want to see Big Bang stuff, I would put my hopes in the pulsar array, for example, on things that are bigger wavelength than LISA. But maybe I'm surprised. It's going to happen in 10 years. So I don't know.
Looking forward to it.
Yeah, thank you.
Hello. Do you know, are there currently any projects already lined up for detection once LISA is in operation in 10 years, or has it not been fleshed out yet?
I think it's fleshed out, yes. There's a LISA symposium happening every 2 years. The last one happened this summer in Dublin. But the next one is going to happen 2026. And there's many different communities working on different aspects of LISA, but the construction is already happening and the data analysis is. There's two main sources for LISA. One is two supermassive black holes. And because they are the same size, numerical relativity is good. But the other one, which is the one I work on, is extreme mass ratio in spirals. So it's one supermassive black hole and one neutron star or one stellar mass black hole. And because of the difference in masses, numerical relativity fails horribly because it cannot, what's the word? Resolve. That's the word. It cannot resolve the different scales. So there's not a plan yet on how to do that part, which, yeah, so that's all the work I've done with my advisor and all the work my colleagues in this specific part of the community are doing are how are we going to model binary systems where one is much less heavy than the other one with enough accuracy such that the templates we get are good enough so that when we filter through a noise, we actually make a detection. So that part, we don't know yet. But most of the other things are already on the making.
Thank you for the talk. I was wondering, for your last slide on dark energy, I guess I can kind of see how you could use gravitational waves to find a redshift and get the Hubble constant from that, but I'm wondering how you would test the density of dark energy using gravitational waves.
Yeah, so it gets complicated, and I was putting a bunch of things under the rug, but there's a big word that I didn't mention, which is multi-messenger astronomy, which is when you can detect the electromagnetic radiation from an event and at the same time the gravitational waves. And when you have the two different kind of channels to the event, you can compare how fast they're propagating to you and if they reach at the same time or one gets some lag because of something. And there's a lot of information that can be obtained from multi-messenger calculations. And one of them is, as the signal is reaching you, was the space between you and the signal expanding or not, at which rate, and things like that. There's also things about dark matter that you can learn from multi-messenger astronomy. But you're right that it's not just with gravity, it's a bit more complicated. But it's still two-body systems. So it's on this sphere of things.
Okay.
Thank you.
Any more questions?
Yes. To what extent, which thing is? So unknown factors that affect, yes. So the question for people on Zoom, because the mic is off, I suppose. Okay, good. So the question is how unknown factors affect this slide that I'm in right now. So the templates. And this is a big collaboration, and there's a whole other community that just does like statistics. And they do a template including, because there's also what we call environmental effects. The binary could be in the middle of an accretion disk, or it could be an accretion disk with dark matter, or it could be, there could be a third object, and it's like a three-body system actually. And people do statistics about how off you are if you include or not include certain effects, and how likely it is that you will still measure something or not based on these unknown effects. Of course, there's the unknown unknowns, and then there's nothing you can do about that. But we know what factors might come into play, which is environmental things, dark matter, a third object, and those things are included in the statistical analysis of these things. When I do my work as a theorist, it's just 2 points. Like they don't even have size. So it's really like the abstract side of things. And then some people do the more messy, which is the more realistic one. Yeah, I don't know if that answers the question. Okay. I'm thinking how to give an answer to this. It's not as much of a big deal as you might think. So in other words, you can still make a detection even if you mess up some of the unknowns, but your capacity to get information from the detection gets kind of messed up, which is good because we will still measure the thing, but then it's like, in astronomy where you see an orbit that looks like an ellipse, and is it actually an ellipse, or am I looking at it at an angle? And actually, I don't know what I'm looking at. That type of thing is what might happen here. So when you make a prediction about, okay, the mass of the black holes was, there's like uncertainty, like was it this or was actually that with an unknown that I didn't know. But it's all included in the statistics, and we will still be able to make detections. Yeah, I will repeat the questions. Yes. Well, yes. So black holes have, I said mass and spin because astrophysical black holes only have those for reasons I will explain in a second. But theoretically, a black hole has all the charges that are allowed in the universe. And that is electric charge, but also color charge, like gluons have color, isospin, or well, all the charges in particle physics a black hole can have. The reason why we don't care about black holes with charge is because if a black hole has positive charge, it's going to suck things with negative charge, and it's going to neutralize. So realistic black holes might have one extra electron of charge, but then they're going to suck a proton and they're going to be neutral, and then they're going to suck one extra proton, but it's always going to be basically neutral. So realistic astrophysical black holes, we don't care about the charge, but the theory is fine, and nature allows charged black holes. I don't know if that answers the question. Okay, good. Yes, somewhere here. Yes. This is a really fun kind of physics problem to solve. When you have a big object and a smaller object, there's the time scale that you take in doing one full orbit, and that scales like the mass of the big one. And then there's another scale, which is the radiation scale, which is how quickly you radiate energy away and then you inspire into the big one. So there's two time scales in the problem. When the two objects are similar size, the two time scales are similar. So there's just one time scale in the problem. The thing takes, I don't know, 1,000,000 years to do a couple of circles, and in 1,000,000 years, it also goes into the primary black hole. When one object is much, much, much smaller, the mass ratio, which typically, if this is a supermassive black hole and the other one is a neutron star, it's like 10 to the 6 or something. It's like a big number. That's the difference in timescales. So you need to do 10 to the 6 orbits before you start spiraling. Does that make sense? You take many, 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 many orbits until the orbit shrinks a tiny bit. And that is like 101 things you cannot do with computers. Like if there's 1,000,000 steps before something happens, you're going to accumulate error in the 1,000,000 steps. Like every time you do one orbit, it's going to be a tiny bit different, and that's going to accumulate. And that's why numerical relativity cannot solve the extreme mass ratio problem, because there's two timescales. One is the orbital, the other one is the radiation one, and those differ by 1,000,000 or more. And there's too many orbital time steps in one radiation time step, and computers suck at doing that. I don't know if that answers the. You do math. Yeah, you have to solve the problem with math. And there's a bunch of mathematics. In the end, you're always going to put it in the computer, but there's more math that you need to do before the problem is well suited for a computer. There's a thing called two timescale approximation, for example, where you recognize that in an orbital path, the radiation is kind of meaningless because it takes like 1,000,000 orbits to radiate a tiny bit. So then you split the problem into two different problems. And you do this mathematical artifact where you have two times instead of one. And there's the physics of orbital stuff evolves with like a slow time. No, sorry, with a quick time. And the radiation evolves with a different time. It's like you go to like 5 dimensions, but mathematically, it's not physically what's happening, but it's like a technique. The radiation evolves with a much slower time, and you solve the problems separately, and you use computers to solve each one separately, and then you combine them. That's one of the mathematical things that you do before feeding a problem to a computer. Yes, you need to be clever in how you express the problem in a way that computers can solve. When the masses are the same, you just chug it. I mean, again, numerical relativity, like people doing numerical stuff would kill me if I said, you just chug it in and it works. I'm sure it doesn't work just like that, but there's less steps than in the other case. Yeah. I think there's a hand, beginning of a hand, yes. I can't, I'm just going to walk, and I can give you the microphone also. I don't know why I didn't do this before.
With Lisa, and how, because it's the wavelengths are so much longer, then there's trouble like figuring out where the direction is. How is that maybe less of an issue with LIGO, if it is at all?
Thank you for the question. I guess the thing I said, is it okay if I'm here and not in the camera? I guess people can still hear me. I mean, you don't have to move. I don't care about, I'm just checking. Okay. So the thing I said, maybe that's what you're referring to, is that in LIGO, the signals last for seconds, and in LISA for months. So they're going to overlap in LISA. Is that what you're referring to? Yeah, so that's why it's not a problem in LIGO, because the events are sparse enough that they don't overlap, because they last seconds. But when they start lasting months, for sure we're going to have a bunch of them at the same time. And then the template thing kind of works, but then we're going to have kind of false positives because there's many overlap. And that's like data analysis and statistics, and I don't really know the fancy techniques that they do, but that's the problem.
Yeah, so first I'll say, like, thanks again for the talk. It was very great and interesting to listen to. So one thing is, we know that near sources of gravity, like a black hole or a neutron star, you have time dilation. Like the time slows down from the point of view of an external observer, like that's at infinity. Like, because the distance is like, you can basically say the distance that the observer is located at, like, is indistinguishable from infinity. Like it goes like asymptotically, like an approximation. So does that mean that when we see something like a black hole merger, that we're actually seeing it happen like in slow motion?
Yes, the answer is basically yes. All the estimates and things I said about like every x-axis that was time is time in the lab frame, like time on Earth. You would have to do the mathematical problem of time dilation to check how much time actually went by in the binary system, but it's something else. Yes. But yeah, that's a part of the prediction part of this. You get the detection in lab frame time, and then you need to do relativity to transform to center of mass time for the system to get the physics of what's actually happening there. So yes, there's time dilation. Any other questions? I can run with the mic.
I really enjoyed the talk. Thank you. I was just wondering, when two black holes are merging together and we detect gravitational radiation from those, is it possible that some of those waves could originate from what was previously inside the event horizon of one of the black holes before the event horizon is rearranged?
Thank you. That's a really cool question. The answer, as far as I know, is no. But there's a big effort that is a bit tangential to this that studies dynamical horizons, because the black hole horizon, when it's just a static single black hole, it's just a sphere. It's really nice, it's really smooth, and we know how it works. But then you can imagine having two spheres and then intersecting them, and it's going to have edges and what's the word in English? Like crevices, is that a word? Like when you have fabric bending in weird angles, it's going to look like that. And then the causality properties of a horizon, when it's all mushed up and like not symmetric at all, is a mess. And there's people trying to understand that. But if general relativity works, the things that are inside the black hole stay inside. Like maybe it's not right and then they go out, but as far as we know, they stay inside. Yeah, because the remaining black hole always has more area than the combination of the two. So it's always encapsulates everything that went in. And the gravitational waves are produced outside the horizon. So it's not that we are seeing information that started inside. They're emitted from the outside of the horizon. I don't know if that answers the question. Yeah, thank you. Really cool question. Any other? It's also 8 if you want to go home.
Okay, so it looks like we don't have any more questions. I should probably stand so I'm kind of visible. Sorry. Thank you so much, everybody, for coming. As always, Fuertes Observatory will be open from 8 to midnight tonight. And the projections have been on or off, and I can't see that well outside. So I don't know if it's cloudy or not, but you should definitely stop by. We will be having lectures about every week with about as many exceptions to that rule as there are weeks that follow it. But definitely look at our website for our future lectures, we will have one next week. But before we end, let's give a second round of applause to Francisco. Thank you so much, everybody, for coming, and have a good evening.